Hey guys, I'm about to do the first of the practice problems in the notes. This is on page 2 of the notes. It's the second slide. It's like a picture of a graph and 4 little questions. Let me share with you guys the screen that has that. There it is right there. You can see this is exactly page 2, slide 2 of your notes. And this is pretty typical of these problems. There's a picture of a graph, which is f of x, and there's like some holes in it, and there's a jump here, and there's some this place. The function is defined when x is 6. The function is defined to be 2 and not 5, even though you would expect it to be 5. But then I ask you to find these 4 limits. So, like I said in the previous video, to find the limit of f of x as x approaches -4, we trace the graph of f of x as x approaches -4 from the left, and we see what y value is being approached. And then we trace the function f of x as x approaches -4 from the right, and we see what y value is being approached. And if those things are equal, then that is the value of the limit. If those things are not equal, then the limit doesn't exist. And there's a couple ways that could happen. We're going to see one here in a second. But let's start with this one. There's -4 on the x. So I trace the graph of f of x, and I approach -4 from the left. And what that y value is going to be, is just going to be the limit as x approaches -4 from the left of f of x. It's going to be equal to whatever that y value is. I'm going to do the same thing as x approaches -4 from the right of f of x. So there's -4, so I approach it from the left, and y is approaching 2. So I trace the function. As x approaches -4 from the left, the y value of that function is approaching 2. So that's this limit here. The limit is x approaches -4 from the left. That equals 2. Then I'm going to do the same thing for this one. The limit as x approaches -4 from the right of f of x. So I start to the right of -4, and I approach on the graph. I trace the graph as x approaches -4 from the right, and I get it's approaching 2 also. So that's good. What that means, when the left-hand limit as x approaches -4 from the left of the function, and the right-hand limit, the limit as x approaches -4 from the right of the function, if those are both equal to the same number, then this limit here, the problem itself, the limit as x approaches -4 of x, is equal to 2. Because these two one-sided limits exist and are equal, that is the value of the limit itself. You can see here that the function itself is not defined when x equals -4. There's a hole. That open circle represents a hole. And this is like a typical example. It doesn't matter that the function is not defined when x is -4. What matters is that as you get close to -4 from the left and from the right, the y values approach the same thing. This concept is very important in calculus, and we're going to deal with it more in this unit. Like I said before, you cannot forget this stuff. So I'm going to erase that, and we will try the next one. I don't know why this thing won't go back to the pen for me. Doesn't really matter. So let's try x approaches 1. So just like we did for x approaching -4, I'm going to say the limit as x approaches 1 from the left of f of x equals something, and the limit as x approaches 1 from the right of f of x equals something. And I'm going to see what the two somethings are. And if the somethings are equal, then that's the limit. If the somethings are not equal, or one is infinite, then the limit doesn't exist. So let's start with this one. Limit as x approaches -1 from the left of f of x. So I go to the graph of f of x. I trace it as x approaches 1 from the left, and I see that the y value approaches 4. In this case, the y value is actually equal to 4 at 1, but I don't care about that. You can see there's a filled-in dot there. That means that when x is 1, y is equal to 4. F of x is equal to 4. That doesn't matter. As I approach 1, y approaches 4. That's why this limit is 4. Now I'm going to come from the right, and maybe you have already guessed, spoiler alert, what's going to happen. As I approach 1 from the right, the y value approaches -2. Unlike the other side, the y value at 1 is not equal to 2. We actually said just a second ago the y value at 1 is equal to 4. There's a hole there at 1 when I come from the right, but that doesn't matter. What matters is the limit as x approaches 1 from the right of f of x is equal to -2. The y value of this function as x approaches 1 from the right is equal to -2. 4 and -2 are not the same. The left-hand limit is 4, the right-hand limit is -2. Since those do not agree, the limit as x approaches 1, the answer to this problem, that limit does not exist. So this is a pretty typical way for limits to not exist. Left-hand and right-hand limits don't agree. And therefore, the limit doesn't exist. So next one, x approaches -5.5. -5.5 is right in here. And even though it's not written there, you got to assume it's 0 because otherwise you have no way to know what it is. So either way, we do it the same way that we did it just a second ago, which is we think about the limit as x approaches -5.5 from the left, the limit as x approaches -5.5 from the right, and we see what value that gives me. I'm super annoyed this thing won't just switch to the pen. Either way, so as I approach -5.5 from the left, the y value, right? I start to the left of -5.5 and I trace the graph. The -5.5, the function value, the y value is equal to 0. And as I approach -5.5 from the right, the y value is approaching 0 again. So that means the limit as x approaches -5.5 of this function is equal to 0. Again, the left-hand limit is 0 and the right-hand limit is 0, which means the limit itself is 0. And whenever you have just like a function that's continuous, like there's no holes or anything at that point, you can really just read the limit off the graph. But just for fun, remember, if someone says prove that that's true, you would say the left-hand limit is 0 and the right-hand limit is 0, and 0 is equal to 0, therefore the limit is 0. Last one, limit as x approaches 6. So I approach 6 from the left. Sorry, x approaches 6 from the left. I trace the graph, and y is approaching 5. And if I approach it from the right, sorry, as x approaches 6 from the right, I trace the graph, and y is approaching 5 again. So this limit must be equal to 5. And again, maybe not again, but just like we saw in the very first example we did in the notes, the first video, like there's a hole at when x is 6, which means the y value when x is 6 is 2. But what matters is as I get close to 6, as x gets close to 6, what does y get close to? And the answer is 5. What I'm saying here is this is true even though f of 6 is equal to 2. Like when x is equal to 6, the function is defined right here to be y equals 2. But the limit as I get close to 6, y gets close to 5. So that's the first example. I will do the next one in the next video.